Well, thank you all again for joining with us. This is the third webinar in our series, and we're going to cover some of the discussion we've already talked about with WaterHammer, but we're not going to spend a lot of time on that because, as I mentioned, this is the third time through. So we'll go over a little bit of background, which you've probably heard a little bit about before, just to bring everybody up to speed. And then we're going to talk quite a bit about how do we mitigate WaterHammer, because that really is what we're trying to do here, is to minimize the effects of this event that can occur in really any piping system. So we'll talk about different ways of doing that. We'll talk about types of vessels, which is really the thrust of this presentation today. And then Scott's going to take you through the details. There's a lot to know. There's a few different varieties of WaterHammer of surge vessels, and they all are used for different reasons. And applying the right one to the right application is critical. It's just like selecting the right kind of car for the work that you're going to be doing, or truck or whatever. There is a lot of options there, and we want to make sure we pick the right one. So Scott's going to take you through that. In the end, I'm going to talk a little bit about the options that we have for surge vessels, as well as take a look at a few installations, because again, it's a lot of variation there. So we do have a lot to go over today, so let's go ahead and get started, and we'll talk about WaterHammer in general. As you've heard before in the previous webinars about this, what exactly is WaterHammer? Well, it's an acoustic pressure wave generated by a change in fluid velocity. And that's a nice way of saying that we have a change in the system. It's a transient event. A system is operating at a steady state condition, and then we are going to change that condition to some other condition. And it might be that we're going to just slow the flow down, change the flow out of the system. Maybe we're going to speed the flow up, or maybe we're going to stop the flow entirely, or maybe we're going to go from a static system into a flowing system. But what we're doing there is creating a pressure wave because of a change in fluid velocity. This WaterHammer is a longitudinal wave. And what we mean by that is typically when you have like if you drop a pebble into a pond, you get a wave that goes out in all directions. Well, with a WaterHammer wave, it's really traveling down the pipe, right? It's moving in a linear direction, longitudinal direction, which is a little bit unique, right? The effects of it are going to be confined essentially to that path of the wave, right? Which in this case would be the piping system. Now, of course, as we go through bends and turns in the piping, the wave is going to move a little bit too. It's going to be reflected off of different walls and affect components in different ways. But in the end, it's still a longitudinal wave moving out from a single source. We call it WaterHammer, but this really can happen in any fluid. It happens, of course, in water, but also happens in hydrocarbons and steams and gases. You've probably noticed it when you're filling up your car at the gas station and the pump shuts off automatically because the tank is almost full, or you're putting a little bit more in, and you see the hose shaking a little bit as you're doing that. This is a WaterHammer event that's going on inside of a gasoline system, right? Because we're changing the fluid from moving through the hose into the tank of the car, and we're stopping it, right? When we open that line again and put more fluid in, we're changing the velocity again. We're getting a new transient event. So there's lots of different reasons why WaterHammer could occur. Some of them I've already mentioned: pump starting or stopping, changing of speeds, stopping one pump while others are operating. But there's also things like that we don't intend, right? Such as power trips. We all want our power to stay on all the time. We have phones to charge and computers to run, but sometimes power does go off. And this happens probably more often in pumping stations than it does in our own personal lives. But it has a very large effect when you shut a pump off instantaneously. You've taken that fluid that's traveling through the pipe and you stop it completely. That's a big change in inertia and momentum. And these can also happen when you have a valve that closes quickly or opens quickly. And a good example of that is a check valve, right? A check valve is in most cases going to slam close. Well, that's an instantaneous change in fluid velocity. And there's also other things like air valve slam that can cause the same kind of thing. Now, you may have heard WaterHammer called different things before. It has a few different names, such as acoustic pressure wave or shock wave or surge. But all of these really are hydraulic transients, which I mentioned before. We're taking a steady state condition, we're changing it to a new steady state condition. The impact of this can be minimal, where like we see when you're putting gas into your car, where it just shakes the hose a little bit, or it could be really catastrophic, where you might have seen on the news water lines, water mains breaking inside of cities and dumping trillions of gallons of water out into residential areas and even industrial areas. We can have supports being pulled off of the walls or pushed out of their mounts. Anything really that's in the flow path can be damaged by a water hammer wave that's large enough to cause a lot of damage. So there's a lot of things to be concerned with here. Even though we don't always hear water hammer happening, if anytime we're going from one steady state to another and passing through a transient condition, we're getting some effect of that. One thing here that I'd like to dispel a little bit is talking about water hammer as a phenomenon. Phenomenon typically means that something is unexplained or unpredictable, whereas in the case of water hammer, we know when it's going to happen. We have clear causes of what it's going to happen, and we can calculate the effect. So as we go on into defining more about water hammer, let's talk a little bit about what it actually means and how we can define it. So on to the next, if you don't mind. Because this is a transient pressure condition or transient flow condition, being able to gather data on water hammer and the effect that it has sometimes requires a really high speed monitoring device. There's a few of those out there on the market, but the one that Blacoh promotes obviously is the surge wave. This is used to take high speed pressure conditions inside of a piping system or any kind of system really to supplement data that you might have from say SCADA or from a monitoring system that you're using for process control. The reason that this is so important is because typical process control units are only looking at taking data maybe once every minute, or maybe in some cases once every 5 minutes, because this is plenty sufficient to be able to control the system and control the process to make the product that it's trying to make. It's a little bit too slow though to catch what we would call transient events like water hammer. We need to take the readings faster, up to 100 times per second. This allows us to see what's going on in the instantaneous pressure changes and get an idea of the magnitude of the water hammer. Remember, I mentioned just a minute ago that in some cases the water hammer might be very benign, right? In the case of the gas pump, but there's other cases where it could be catastrophically damaging. And those kind of conditions we need to be able to quantify, and transient pressure monitoring allows us to do that. It also allows us to calibrate some of our transient models, which we'll talk about in a few minutes, when we're sizing vessels or sizing mitigation components. Knowing the magnitude of what we're dealing with has a big effect on what kind of components we need to select, and in some cases, how many. We may need to actually stack some on top of others, not physically, of course, but in the system where they have a effect for under different conditions because the pipeline or the system may go through different transient events depending on how it's operating. Moving on to the next, let's talk a little bit about how to mitigate the surge. So if we look at the equation off to the right there, this is what's commonly known as the Joukowsky equation. You've probably seen this before in previous webinars, maybe you've done some research on it before, but we can use this to understand what we can do to mitigate surge or water hammer. By looking at the right side of the equation, we see there's a couple of terms there that we can do something about. Well, in most cases, fluid density, we can't change, right? That's the fluid that's being moved in the line. That's a requirement of the system. We can't do much about that. But wave speed and the change in velocity or acceleration are controllable to some degree. So there's ways to slow the amount of velocity change. Because this is a change in velocity, we can slow that process down. We can still bring the fluid to a rest, but instead of doing it instantaneously, we can change maybe a VFD ramp time or the valve closing or opening speed to stretch that out to reduce the acceleration and therefore reduce the amount of pressure rise that we get in the system. We can also decrease the wave speed. This is the wave speed of sound inside of the fluid and piping system. So by changing the materials from steel, for example, to PVC, getting a less rigid system, the wave speed is going to go down. The same thing is true by adding flexibility to the piping. If the system is not quite as stiff, then we can absorb some of this energy and maybe not even create quite as much. So by changing the system a little bit, we can reduce the effect or reduce the pressure rise that we get from water hammer events. However, in some cases, these are not possible, right? A VFD might not be available for the system, the valve might not be able to be adjusted, and the materials for the pipe might be set, so we're kind of stuck. So what do we do in these applications where we really can't adjust the wave speed or the change in velocity, and we still need to be able to mitigate the effect of the water hammer events? Well, we can adjust the pump inertia a little bit by having the pump slow down a little bit over a longer period of time. We can add vacuum valves or surge anticipating valves and even special check valves that all help to reduce the effect of the water hammer on the system. But what we're going to talk about primarily today is surge vessels. Now, surge vessels can be used, of course, for water hammer protection, but they also have some other benefits, such as pulsation reduction and pump cycle control, and even allowing for thermal expansion. So that's what we're going to spend so much time on this today. Water hammer is a complicated subject. We've talked about it a lot over the last two webinars. We've talked about it again today. There's a lot to cover. We want to make sure that we're giving you all the options possible when you're trying to mitigate this problem in your facilities. So moving on to the next, let's take a look at a couple more things before we get into the vessels themselves. There are a few different vessel types, and this is what Scott is going to go over as he gets into the more technical portion of this on the vessel side. The first one we're going to talk about, of course, is bladder vessels. These have an internal bladder, or kind of like a balloon, that eliminates the need for an online compressor system while allowing some dampening inside of the system by either compressing or expanding the balloon. There's also hydropneumatic vessels, which are very similar to a bladder vessel, but they don't have the bladder inside. There is an actual contact between the liquid and the air that's inside the tank. But again, it's providing some dampening, some cushion, if you will, for the energy that's being generated inside the system. We also are going to talk about dipping tube vessels, which are a little bit more of a special way of doing this when you have a valve, or rather a pipe inside the system that almost kind of charges itself. And I'm going to let Scott get into that because he's much more of an expert on the dipping tube design than I am. But the idea here is for special applications, a dipping tube might be the best choice. Now, all three of these, as I mentioned before, have their places where they fit and where they don't. And applying them correctly is very important. We'll talk about that as we get towards the end of the presentation. One thing I do want to mention here, though, is in all of these cases, we're mitigating the surge, right? We're not eliminating it completely. There is still going to be a transient condition where the fluid is changing from a steady state condition previous and then a steady state condition after the event has taken place. All of these different vessel types are going to be used to mitigate the effects of this on the system. It's almost impossible, and it is primarily impossible to eliminate water hammer completely. We can only reduce its effect. So moving on to the next slide, we'll talk a little bit more about the do's and don'ts before we get into the vessels themselves. One thing we want to pay close attention to also is communication time, which we've talked about in the past, and this plays into how and where we locate the vessels. Now, communication time is basically how long does it take for the wave to travel from its point of origination or induction point all the way to a point where it can reflect and come back towards the source. This is a function of the length of the pipe and the speed of sound in that pipe. Very simple calculation, but the reason that we spend so much time talking about this in previous webinars is because it has a big impact on the magnitude of the water hammer event. When the closing time or the event time is smaller than the communication time, you're going to get a much higher pressure rise than you would if the communication time is shorter than the event time. As we talked about before, slowing valves down, slowing pumps down when they're coming to a rest allows us to extend out the event, the transient time, to be longer in most cases, we hope, than the communication time. This reduces the effect of water hammer. It's not always possible, but we do try to do it when we can. It also allows us to think about how do we want to position the surge vessel. We want to have it as close to the wave induction point as we possibly can, because now we're getting that communication time to that first dampening device as short as we possibly can. This allows us to have a faster event when it happens without having the same very bad negative effects on the rest of the system. There's some other things there about sizing the vessel and thinking about the root surge issue. What's actually causing the problem? And will a surge vessel actually fix it? There's a lot of transient analysis that needs to be done to actually size these vessels correctly. And it can be a complicated process, but it's worth the time. If you're seeing damage or you're seeing short pump life or you're seeing replacements of components that continue to break, spending the time to do the transient analysis and locating and selecting the right kind of vessel can go a long way to saving you a lot of maintenance costs and a lot of headaches. What we also need to make sure we don't do is only size for one condition. There's lots of conditions that pumps run in, lots of conditions that pipelines and other systems run in. Another example, going back to cars, is we don't get into our cars and drive full speed all the time to get to work and then stop the car immediately. We drive at lots of different speeds, right? We're stopping at stoplights. We're going on streets that have a speed limit of 35 miles an hour and some that have a speed limit of 65 miles an hour. So these are all different conditions that our cars see. Well, the same thing is true for a pumping system. It's going to see a lot of different conditions across the course of its life. It may have a rated point or a duty point that we design around for sizing the pump, but we also know it's going to operate in a wide range of conditions. We need to size the surge vessels and surge components for all of those conditions: high flow, low flow, static, vacuum conditions. All of these different things can play a role. So I've talked a little bit about some review on water hammer and what we can do about it, but I really haven't touched much on the vessels themselves except to give you just a list of them. So I'm going to turn it over now to Scott, and he's going to take you through all the different options for the different kind of vessels that we've talked about are listed out already. Go ahead, Scott.
Thanks, Chris. Thanks for the water hammer review. Howdy, I'm Scott Bradley. I'll be taking you through the 3 different types of surge vessels, and we'll get a little more detailed into the types. So what does that vague accumulator node in your transient model actually look like? Hopefully this webinar will give you a realistic picture of that and give you some of the highlight some of the limitations of each type, help you understand a few different configurations, give you some design considerations to help you select and specify a vessel for your application. So to begin with, we'll look at this hidden view drawing of a typical vertical gas and bladder vessel. And just to let you know, each vessel type we're showing is considered to typically it tees into the line with this inlet outlet connection here at the bottom, whether it be one or multiple. In each vessel type, the liquid somehow compresses gas in the vessel, like Chris mentioned, which changes your system from incompressible to being compressible, and the energy is immediately available, as opposed to a valve, like a spring-operated valve, that may not be able to immediately respond or won't immediately respond. You know, it has some reaction time there, and with the wave speed we're talking about, it wouldn't be able to react in time. So you need some kind of immediate energy source here. So with this bladder vessel in particular, being gas in the bladder, the bladder shape is actually typically the full volume of the vessel. So the flange of the bladder can be used as the gasket in a lot of applications, between the blind and the nozzle here in this manway or access opening connection. And here at the top, you have your air charge line, and you typically have some kind of charging manifold to help you pre-charge the bladder before you bring it online. And then here down at the bottom in this inlet outlet connection, you have a few branch connections for this configuration in particular. A drain connection, a PSV, and instrumentation. So you want to be able to drain the vessel before, on the vessel side. of the isolation valve. So you want to have an isolation valve between your main line and your surge vessel, and you want to have a way to drain it and maintain the vessel. And then for your instrumentation, typically you are wanting to look at liquid level. And I'll give you a better picture of what that looks like in later slides. So this next configuration here is liquid in bladder. The bladder is connected to these two bottom inlets. They're inlets and outlets, as opposed to a flow-through design. They act as the inlet and the outlet. So the liquid goes into the bladder and compresses the air. The air is actually on the shell side this time of the vessel. This one in particular is horizontal, but they can be vertical as well. And let's see. So some typical issues with this one is bladder bunching up on the inlet nozzles. And what you can do is tie them up at a couple of points at the top of the vessel. And whenever you're selecting a vessel design, you want to keep in mind age of water in certain applications. Depends on daily pump operations. You don't want to have a vessel that comes far from one of your inlet outlets and create a dead leg where you don't really have any circulation. So an exception can be taken for the horizontal vessels if you have a hydropneumatic vessel with circulation and flush ports. But typically you don't have those in a bladder vessel. And then whenever you're going to design your whenever you're trying to figure out your diameter and length of a vessel, so typically you have a volume that's required from your transient analysis, but that could be any length or diameter. You don't really know what to choose. So there's a few tips on that. Our general, it's just a real general rule of thumb, is you want to keep your overall length to diameter ratio less than 3 to 1. That's just due basically to the weight load of the bladder itself if it's suspended on a vertical vessel, and age of water issues on a horizontal vessel, hydraulics, there's a few reasons to that, but we typically try to keep it less than 3 to 1. So if you do know the volume you need and you're trying to figure out your diameter length pair, there are usually dimensional constraints, especially if the vessel is going into a vault or a pump house or some kind of building. So those can sometimes drive your choice. Also keep in mind that bladders are wear items, and although they do last well in most applications, they do eventually need to be replaced. So keep enough access room around manways, and if it's a liquid and bladder configuration like this one, you want to keep sufficient access to the inlet nozzles as well. Also, the vessel heads are typically forged in 12-inch diameter increments, here in the US at least. So from our experience, a lot of times it is cheaper at these length to diameter ratios to go with a smaller diameter vessel, even though it may be longer for the same volume. It can be cheaper than a large diameter vessel due to the more expensive and sometimes thicker heads. If you have any questions about these things, or selecting configurations or determining an optimal dimensions, you're welcome to reach out to us. We can provide some practical guidance for your specific application. The other thing about bladder vessels is they typically have some sort of internal coating for protection of the bladder. Um, so in fabrication, there's always rough spots in the metal, um, sharp areas that can uh, cause problems for the bladder. So even with sandblasting, um, that you can still have some rough spots after that. So a good high build internal coating is good to provide a smooth surface on the entire inner surface of the vessel. Um, so here's a few pictures on assembly. So on that, this is actually that last vessel that we just looked at. Um, we're loading the bladder in through the manway and pulling the flange of the bladder through that inlet nozzle, and then tying it up like I talked about at the top. And then one thing I didn't mention yet is that is an issue with bladder vessels is extrusion. So you want to with these bladders, they like to open up like Chris said, they're like a balloon. So they need to be carefully cradled in all of the surface that they want to open up to. So we install these inlet screens on that inlet nozzle. I'll go back to this slide to show you in this inlet nozzle connection right here. To and the screen goes up to the bottom surface of this vessel to cradle that bladder and keep it from trying to extrude through that inlet nozzle, maybe on a vacuum condition or on the when you're pre-charging the bladder. The other thing I didn't mention earlier was with a liquid and bladder vessel configuration, um, those branch nozzles can be an issue. So one way you can take care of that is to provide inlet spools. Just a simple pipe spool here between the isolation valve and the vessel so that you can get these other connections, the drain, the instrumentation, the PSV. A couple of other ways to do that is with bleed rings if your drain size is not too big, or you can just do that on the end user's pipe. In this one in particular, the manufacturer built the inlet spools, but that needs to be coordinated, whomever chooses to do it, because those connections are important. Okay, here is that same vessel. Actually, it's an identical one. And it's potable water, 6,000 gallon. It's got level and transient pressure monitoring. And this is showing that control panel where that's housed. And it's in Louisiana. So I mentioned before that the bladder can be used as the gasket in a lot of applications. But if you don't want to use the bladder as the pressure containing gasket, you can use what we call catching flanges. And what those do is they allow you to they sandwich the bladder, and then one piece of it themselves is sandwiched in the blind flange and the nozzle, so that uh, the catching flange assembly is the pressure containing component. A double catching flange can be used on an inlet and manway configuration, and that's recommended for hydrocarbon liquid and bladder so that you can purge the bladder of air before the vessel is brought online, or if there's a concern of air pockets forming inside the bladder during operation. Um, so and here's an example of one that uses a catching flange. You can't really see it because it's pretty small up in the manway connection. But these are a couple 7,500 and 10,000 gallon vessels in petroleum service in Texas. So that's kind of showing you the bladder, but I want to get into pre-charge and some of the limitations there. So let's see. This is a snapshot from our liquid level tool that we call surge level. It allows design engineers and field operators to be confident in the pre-charge pressure when all you have is the current pressure and the associated liquid level. It's based on Boyle's law, P1 V1 to the N equals P2 V2, that's pressure and volume, to the N, which N is the polytropic constant. The polytropic constant's 1.4 for diatomic gases such as nitrogen and air for quick volume changes. If the change occurs in more than a few minutes, the constant is more like 1.0. We typically assume the most conservative for liquid level applications, which is 1.0. However, a mid-range value of 1.2 may also be used. And so for bladder vessels, the bladder does not like to be scrunched up and compressed up into the top of the vessel, nor does it like to be operated at fully open all the time. So our recommendation there is to keep the bladder between 20% volume and 80% volume, or you can think of this as the middle 60%. For bladder vessels. For hydropneumatic vessels, since there's no bladder, the recommendation is more like 90-10. To keep you want to keep a liquid seal at the bottom of the vessel to keep from bringing air into your system. So this is a minimum line pressure calculation and a maximum. So using this, we can tell you the line pressures that are problematic for the bladder and give you an ideal range that you want to work with within to prolong bladder life. We can issue you a liquid level report that shows a comparison graph of different precharge pressure possibilities and their ideal line pressure ranges. Sometimes a bladder limitation may be revealed at this stage, and the engineer may choose to iterate the vessel sizing or adjust the model. Here's a snapshot of the tool for a horizontal vessel. The thing to note here is the 150 psi design pressure. And this one is just showing you that that same vessel at minimum and maximum pressure, and it's showing a couple of warnings. So our tool is flagging the 80% limitation that we specified earlier. Like I said, 20% to 80%. But don't forget that at pressures less than 20 psi in potable water applications, the city may need to issue a boil water notice for unsanitary backflow concerns. So, and then if you go above the max pressure, our tool will flag you, of course, if this is showing 138, but it's actually running the 1.0 polytropic constant in the background, even if you enter 1.2 here. So we're just showing that this is reaching both the 20% gas volume limitation and the MAWP of the vessel itself at this line pressure and precharge. Just to show you that there's other considerations. I know this is kind of a rabbit hole into liquid level calculation, but it goes to show you the kind of checks that we go through to make sure the prescribed pressures and levels are actually feasible, ideally in the design phase. Um, the next surge vessel actually has a few names. It's called a hydropneumatic vessel, or air over water, or simply a compressor vessel. Since there is no bladder, the air directly interfaces with the water or other whatever the processed liquid is. It uses a compressor to replace that air that gets dissolved in water over time. The liquid level is typically controlled by an add air solenoid valve that brings higher pressure air from the compressor to the surge vessel, and a vent air solenoid valve that puts air into the atmosphere when the liquid level gets too low so that it can bring the liquid level up. Some kind of liquid level measuring device is used, whether it's guided wave radar or level switches or differential pressure transmitter, etc. A controller or relays are used with or without delays to determine when to actuate solenoid valves. The compressor is sized to keep up with the dissolution rate. Typically, the governing criteria is that it must be able to recover a lost charge in a specified time frame, usually minutes after a return from a power failure. So as with anything, there's pros and cons. So now that we have two vessel types, we'll primarily look at pros and cons from hydropneumatic to bladder vessels. So with hydropneumatic, um, you can get to the much larger vessels, assuming your compressor capacity can keep up with it. And because you don't have a bladder in it, you are less concerned about internal coating that you're wanting. You don't need to protect a bladder with your internal coating, and you don't have to worry about extrusion, bladder extrusion, so you can put nozzles anywhere you want. Some cons with hydropneumatic are the maintenance costs. So with anything, like with your, I'll use Chris's example with your car. You got to change your oil on it all the time. You got to uh, the compressor needs its oil changed. You need to change out the air filters, um, oil filters. Any kind of moving part. Uh, what what's the saying? Whatever could go wrong does go wrong sometimes. So this could become quite a bit of a total project cost over time. Um, Another con would be the compressor and controls could be an upfront charge, could be expensive. It's not usually expensive for low pressure applications or low pressure and low CFM. But for high pressure and oil-free compressors, your price can get pretty high, and even get in some cases we've seen it be as high as the vessel itself. And especially for flow-through vessels, as opposed to teeing the vessel into the line, right? Because you have much more water turnover. So you have a much higher dissolution rate. The other con here is the precharge variance. So since the compressor comes on and off at set points, there's a controlled range of precharge pressures as opposed to a single set it and forget it precharge pressure in bladder vessels. Typically, this range is determined by pump operations, liquid level control settings, and vessel volume. For example, a pump that doesn't come on for a whole week could mean I'm sorry. A pump that doesn't come on for a whole week could mean a significant amount of air dissolved if the add air level set point is not reached. If your system is sensitive to varying precharge pressures, this could be problematic. Transient pressure monitoring, as Chris displayed earlier, surge wave is our product. This can be used to see how the system responds to different precharge pressures, if that's a concern. Here's an example. This one's high pressure. This one's actually in a mine for mine water, 1,000 psi in Mexico. You can see the guided wave radar transmitter up here and the sight glass to view the liquid level. The air line runs through comes from the compressor and it goes behind the vessel. You can't see it, but there's solenoid valves and then back into the top of the vessel here. The programmable controller receives a pressure signal from the pressure transmitter and a level signal from the guided wave transmitter, and it decides when to actuate each solenoid valve with a time delay. For hydropneumatic vessels, the air gets added while the vessel is online, so the associated precharge pressure must be determined from the liquid level and operating pressure rather than directly measured. When the operating pressure range is small enough, the precharge pressure range can reasonably be determined from just liquid level. However, for this example, the liquid level changes considerably over the operating pressure range. As you can see on this graph, the pressure goes from 730 to 830 psi, and the midpoint between the add air and remove air set points changes about 2 inches. So this controller uses a different set of level set points based on the measured pressure to supply an accurate air charge. Last but not least, our third and final vessel type is the dipping tube. This vessel has neither a bladder nor a compressor. It consists of an air vacuum valve connected to a tube that extends down into the vessel. The length of the tube is calculated based on the required air volume from the transient analysis. When the vessel is empty, the air vacuum valve is open. So the vessel is at atmospheric pressure. When the liquid comes up to the tip of the tube, the pocket volume, or this annulus sort of shape here, gets trapped and compressed. This makes the liquid rise quickly up the tube when the liquid goes up from the tip even further. So then when the liquid gets to the top, it closes the air vacuum valve. So then you have a closed system, right? You have effectively a 0 psi pre-charge vessel. So then when the pressure goes back down, tube empties, the valve opens, and the vessel is recharged with air. So because this is a 0 psi pre-charge, it's for low pressure applications only. It's not for hydrocarbon applications, right? Because you're using air. It's not typically sized to completely empty, and you want to consider a dipping tube vessel if the bladder vessel is emptying, regardless of what you're doing with the volume. So as with any valves, they require maintenance. So just keep that in mind when selecting a vessel type. So your air vacuum valve will need to be part of your valve maintenance schedule. So whatever can go wrong to valves could make your vessel not function properly. So another concern here is vessel settling. If you're not anchoring this to a solid foundation, that can cause the valve to not seat properly. And then here are some examples. Here's a dipping tube surge vessel that's actually composite material, and it's located in Virginia. And here's a pretty tall one that uses a transient pressure monitoring. And this one actually has a small compressor that is used to replace the air dissolved in liquid. So it's actually kind of a hybrid vessel. And then here's another example of a dipping tube, just showing how it's assembled with here's the fully assembled picture here with the tube in and the valve installed on top. And this one is for wastewater in Texas. So that's it for the vessel types. Now I'll hand it back to Chris, who will wrap up with an application chart and, if time permits, more examples and a summary.
Thanks, Scott. It's good to go through all of those and see all the pros and cons and where they might fit. So if we go to our next slide here, we have a chart that shows exactly what kind of applications fit for different kinds of vessel types. And it's hard to keep track of everything as you're going through it, but we try to lay this out as cleanly as we can. Now, there's other applications, of course, that might not fit directly into this list, but it gives you a basic idea of what kind of vessel type you might be looking at and what are some considerations. Scott mentioned a lot of these along the way, but there are some things that we want to avoid and some things that we want to gravitate towards depending on the application. So I'm not going to go through this in detail. You're welcome to take a screenshot of it, or you can take a look at it when you get the slides from the webinar. But this does give a little bit of an idea of where we'd like to go. And as Scott mentioned also, there's a lot of different options for the way that the vessel is designed depending on the application. So it's not just limited to this application chart. As we go into the next slide, we're going to talk a little bit about what we call appurtenances. So if you look at the vessel itself and you think about how we're going to connect it to the system, there have to be some connections there. Let's see if we can get that to scroll to the next one. There we go. Thank you. So the vessel can have whatever connections are necessary to be able to adapt to the system that's going into. Now, of course, Blacoh has some standards that we stick to, and that's what we quote, but we can modify vessels as needed to be able to make them fit into the system that you're using. This can include things like drains and pressure safety valves, connections to compressors, connections to other parts of the system, and all of these things can be included in. Of course, as we add more and more connections and more features to it, the price changes. It's going to become a little bit more expensive to add all these things in because it takes time and materials. But there's always options to be able to make it fit to the system, even if we need to deviate from the standard designs. Let's take a look at a few examples here. But first, I forgot about this. We need to talk about pre-charge. Scott mentioned this a little while ago too, and when he was talking about the liquid level calculations. And pre-charge is one of the most important things that we talk about. Sizing, of course, is important. We get that through transient analysis. We talked about where we want to locate these vessels in relation to whatever's causing the water hammer event. And then the last one we look at really is charge. And the reason this is so important is because it's giving you it's telling you how effective this vessel can be under the range of conditions that you're going to see. And there is some guidance out there in the world. This is an article written in Pumps and Systems, I believe, about how to pre-charge a surge vessel. And it's a complicated issue, just like all these water hammer issues are, but there is information out there that's available, and we follow these guidelines, right? We've used these for a long time ourselves, and we continue to use them in our liquid level calculations. Moving on to the next slide, just a couple of applications. Scott showed a few already. I'm just going to show a few more examples. This is a 3,000-gallon bladder vessel that's installed in petroleum services. As we mentioned, water hammer is not just for water. It can act in hydrocarbons too. So this is a situation where there was a transient event that was causing some damage, but it was a hydrocarbon application. So we size the vessel appropriately. A sewage vessel. This again is bladder, but now you can see this is actually located in a vault underground where the sewage system is. So it's a little bit more unique. It has some special connections to it, but we can size it for that application as well. Moving on to the next, some smaller vessels. These are sized for processed water and located in Louisiana. So again, bladder vessels, but a wide range of applications. We can use them in hydrocarbons, sewage water, drinking water, all kinds of things. Wherever we have a transient event that's causing damage to the system because of the speed of the transient, a surge vessel might be something that can help us out. So I think the last thing we have to talk about here is the control panel. And Scott mentioned this and showed a couple of pictures of it as well. The control panels typically come with the vessel with transient monitoring installed, like we talked about with the surge wave, but they could also include instrumentation to monitor liquid level or to control a compressor if it's that kind of vessel. And these can be mounted onto the vessel itself or nearby. One of the pictures Scott showed was nearby. And these are also supplied with the vessel as part of the appurtenances. So lots of different options here. And again, as I mentioned before, able to be adapted to the application that it needs to go into. So I think that is pretty much all we have to cover today. So we've covered a lot of things, and we started off talking about water hammer and how complex it is, that we do need computer modeling to figure out what we need to use, and how important transient monitoring is. We know that we can use computer modeling to get an idea, but there's really no replacement for being able to read the pressures directly and know that we have the right answers. This can help us to calibrate the models as well as size search vessels. And any of the three types, right? Bladder, hydrodynamic, or dipping tube can all be sized using transient analysis and transient pressure monitoring. As Scott mentioned, surge vessels are designed to give and receive energy to protect from high and low pressure waves. We often think about water hammer as only a positive pressure wave, but if we think about what happens around that point of induction, there's a positive pressure wave on one side, and then you're going to turn it into a negative pressure wave as the fluid goes into a transient condition. And on the upstream side, it could be in a negative condition already. So we need to have a vessel that can both take energy from the system and then give it back when necessary. And surge vessels can be used in lots of different applications. There's application groups, there's application conditions that we want to look at to size them properly and to pick the right kind of configuration. As we talked about before, we don't all have the same car. We all have different things, but we have certain criteria that fit for different applications. And the same thing is true for surge vessels. So moving on to the end here and making a little bit of time for questions, we hope that you've learned a little bit more about surge in general and also specific kinds of surge vessels. And we're welcome and open to any questions you might have about this topic, or surge vessels in particular.
This was great. Really well put together, guys. I thank you. We do have one question from Gerard. Is there ever a need to have a vessel at both the pump end of the pipe and at the other end where a valve would be?
I think the answer is yes. I'll let Scott elaborate.
Yeah. So if it's close to the pump, it can be used to help on pump starts, pump trips, and then if it's over by a valve, like if the valve is your is causing a water hammer for whatever the reason, if it's from closing it or opening, I mean, either way, opening it or closing it can cause a water hammer. But what I mean is if the valve is the problem as well, you can put a surge vessel close to it. So if you just had a surge vessel close to your pump, it may not really help you down over close to the valve, and vice versa. If you had a vessel by your valve, it may not help hydraulically over by your pump.
And one more thing I'll add to that too. This is where transient monitoring and transient analysis really comes in handy, right? Because you may not know for sure where the problem is originating or that you're covering all of it by adding just one. The monitoring system can tell you, are you getting pressures downstream that are not being dampened by the surge vessel upstream, and modeling the same way, right? You put the whole system in and you can look at the pressures along the line.
You mentioned that the dipping tube type of vessel is for low pressure applications. Is there a differentiation between the bladder and the compressor type?
As far as pressure goes, you can get high pressure, as I showed, a hydropneumatic vessel that was 1,000 psi. But bladder vessels can go that high as well. The issue with bladder vessels can be the high precharge pressure. As I mentioned on the anti-extrusion screen. Sorry, that's hard to say. The bladder, whenever you're going to precharge it, is going to want to extrude through whatever you're holding it up with that screen. So we generally like to use a two-phase precharge procedure whenever there's a high precharge pressure, so that there's a liquid barrier there to keep the vessel off of the screen. Because sometimes with a precharge pressure that's very high, it can even the screen can damage your bladder. So if you use it correctly, you can use a bladder vessel for high pressures as well.